everybody, and welcome to our third video lecture for group schemes. Today what we're going to talk about is sheaves and sheafification. As we saw from the previous lecture, this is a really powerful tool that allows us to define a lot of the objects that we see in regular group theory, extended into the context of affine group schemes. For those of us who have some background in algebraic geometry, we're probably already familiar with some ideas like sheaves and pre-sheaves. And for people that are coming from that point of view, things are going to switch a little bit. Pre-sheaves are being replaced with functors from K-algebras to sets. Sheaves themselves are going to be replaced with functors that have two very nice properties. Specifically, they have a uniqueness property and a gluing property. And these correspond precisely to the uniqueness and gluing properties that we see distinguish sheaves from pre-sheaves. In particular, the representable functors are going to necessarily be these functors with this uniqueness and gluing properties, which these latter functors, of course, we're going to be calling sheaves. So in particular, for us, representable functors will be sheaves. This isn't to say that every sheaf will be a representable functor. Sheaves are kind of a larger class. But in a lot of our constructions that we were talking about last time, we were writing down some functor, realizing that it wasn't representable. And through this process of what we're going to call sheafification, we're going to create from any particular functor an actual sheaf, which is a new functor, but with this uniqueness and gluing property. And in those particularly nice situations, the new sheaf that we create will turn out to be a representable functor, giving us those constructions that we wanted before. So that's kind of the great plot here. And a great place to start, I think, with this whole discussion is to just back up and think about what a sheaf is on a topological space. If we think about everything in that context, the definitions will be much more strongly motivated. So for sake of our discussion, I'm going to let X be a topological space. Just think about your favorite topological space. It could be R or C or A1 or P1 maybe, whatever you like. One thing a topological space always has is open sets, and we can make those into a category. The objects of this category are just going to be open subsets of X. And the arrows are going to be inclusions. So U has an arrow to V if and only if V is a subset of U. In this context, a pre-sheaf is just a functor from the category of open sets to the category of sets. And for sake of consistency, let me go ahead and adopt the convention that I'll underline open, because throughout here, all of my categories have ended up being underlined to distinguish them. In particular, if V is an open subset of U, which is an open subset of X, then there's an arrow from U to V. So the functor F determines an arrow from FU to FV. Since the arrow from U to V is unique, the arrow from FU to FV is also unique, and we describe it as the restriction from U to V, denoted RES U, V. As a shorthand, if I've got some element S of FU, the image of S under the restriction map from U to V is often denoted as S restricted to V. Now a sheaf is a pre-sheaf which satisfies two additional axioms. The first axiom is uniqueness. This says if I have a covering of U by open sets, then the induced map going from F of U to the product over all i's of the F of V i's by sending something in F of U to the tuple whose elements, or entries I mean, are the restrictions, is injective. Another way to say this is that the value of an element in F of U is determined by its restrictions on a cover, and determined uniquely in this way. The second property we must have to be a sheaf is gluing. This is to say, if I have a covering vi of u, and I have some sections defined over the vi's which agree on the overlaps, then I should be able to glue those all together to something inside of f of u. And I just used a word there accidentally that I was trying to avoid, but let me go ahead and adopt it anyway, since it'll be hard to resist the temptation. We oftentimes call the elements of f of u in this context sections over u. So what gluing tells us here is that, again, if I have a covering of u, and for each open set of my covering, vi, I have some section si over vi, i.e. some si in f of vi, which agree on the overlaps, which is to say that when I take si and I restrict it to si vi intersect vj, I end up with the same thing as sj restricted to vi intersect vj. In this case, they can be glued together to a section over u, whose restrictions to each of the vi's are the si's. So these are the two properties I want in order to make a pre-sheaf into a sheaf. Let's consider a very simple example. In this case, I'm going to take X to be the topological space, consisting of 2 points, P and Q. And we'll take our topology to be the discrete topology. Further, let's go ahead and let S be the set, consisting of values 0, 1, 2. I'm going to define a functor from the open sets on X, the category of sets, and what it does for any particular object is it sends that object to the set S. And for any morphism between sets, the associated restriction map from U to V, I'm just going to take to be the identity map on S. And it's very easy to see that this is a well-defined functor from this category of open sets on X to the category of sets. However, this does not turn out to be a sheaf. The problem in particular here is gluing. For example, I can think about the open cover of F consisting of the open sets which are singletons P and Q. Then if I take the section 1 inside of FP and 0 inside of f of q, and I forget, I need to add one additional property to my original functor. In particular, it needs to behave a specific way with respect to the empty set. And what I require here is that the empty set return just the set consisting of a single element 0. And the associated maps are the constant maps. So in particular, the restriction of 1 and 0 to the empty set agree. So 1 and 0 agree on the overlap. Of P intersect Q, which is the empty set. So if we could glue, there should be some section inside of f of x whose restrictions to P and Q agree with the sections that we already chose. However, the restriction map here is the identity map, so this does not exist. And this is why gluing doesn't work. So now that we looked at an example of a sheaf where gluing doesn't work, our pre-sheaf where gluing doesn't work and therefore we don't have a sheaf, let's also look at some examples of sheaves. Our first example, let's take Y to be a topological space. And I'm going to define a functor from the category of open sets in X to the category of sets, which takes an open set and sends it to the collection of continuous functions from that open set to Y. If V is an open subset of U, that is to say, if there's an arrow from U to V, then the induced morphism, or arrow, from CUY to CVY takes a function and sends it to that function restricted to V. This is sort of the canonical example of a sheaf. And in particular here, the restriction map is literally restriction. At this point, it makes sense to try to do the schemy version of things. Here, we replace our space X by a ring. In this way, morphisms from a space Y to a space X are replaced by arrows from our ring A to our ring B in the opposite direction. If we're working over a base field K, this is from a K-algebra A to a K-algebra B, or a base ring K, if we want to be very general. Note in particular that the arrow reverses direction. Open sets of our original space X become localizations of the ring A. So to be able to define a pre-sheaf, that is some sort of functor on the category of open sets, we need to define a functor from the category of K-algebras to the category of sets, or even more specifically, a functor from the category of K-algebras, which are isomorphic to localizations of A, to the category of sets. However, it turns out to be nicer to be more flexible and just begin with a functor from the category of K-algebras to the category of sets. And we can always take a functor which is defined on localizations and extend it to some sort of functor on the category of K-algebras to category of sets. So really nothing is lost through that process. And now what we need to do is we need to figure out, now that we have some idea of how to define a pre-sheaf, what we should impose as our constraints to distinguish sheaves from pre-sheaves. We need to figure out in particular what the appropriate translations of the uniqueness and gluing properties are. To do that, let's think about an open covering given by a bunch of VI's of an open set U. This in turn corresponds to a bunch of localization, or a big collection of maps from A into BI, where the BI's are localizations. The fact that it covers means that the natural map from the disjoint union over I of the VI's to U is surjective. But this amounts to the same thing as the map from A into the product over I's of the BI's, this product here representing the disjoint union before being faithful. This is exactly one of the concepts that we explored in a previous lecture. The idea that these guys are open subsets translates to some property about these guys being open embeddings as far as rings go. But as I mentioned before, in this context, we gain a lot by not being so restrictive regarding what we think about as being open sets and restricting all our ideas to thinking about open. And one particularly nice way to translate the property of being an open map into a sufficiently broad interpretation in this new category is to replace it with flat. So we're looking in particular for maps from A into a product over I's of the BI's, which are both faithful and flat. Of course, this should resonate with the property of being a quotient map that we were talking about before. And now the uniqueness property was the property that the map from f of u into the product over I's of the f of VI's is injective. This becomes the very same property over here. The natural map going from f of A into the product over I's of the f of BI's must be injective. So this is the gluing property. It's that this must hold true whenever I've got a map from A into a product over I's of the BI's which is faithfully flat. The gluing property is also similarly straightforward. The only catch here is we need to also interpret what it means to take an intersection. If V and W are both subsets of U, then their intersection, V intersect W, will of course also be a subset of U. Translated over to the ring side, I'm thinking about maps from A to B and A to B prime, and the intersection is determined by the map from A to the tensor product of B and B prime over A. So our gluing property was that if I have an open cover of U and sections over each set in the open cover such that they agree on their overlaps, then I can glue them together to a section over U itself, whose restrictions are the sections over the open cover elements that I found before. This translates in the obvious way that we talked about. I'm replacing my open cover from a map A to a product of algebras, product over IBI, which is faithfully flat. My section over FV is turning into a section over BI. Oh, and I realize I have a typo over here. There should be VJ intersect VI. It should be VI intersect VJ. And our condition that they agree on the overlaps become that for all I and j, the restriction map, which goes from BI to BI tensored over A with BJ, takes SI to the image of SJ under the corresponding restriction map. This here being a J. This is going from BJ to BI tensored over A with BJ. And our condition then is again that there exists a section S of F over A, so that the restriction map from A to BI of S is equal to SI for all I. So to summarize, we have the following definition. A pre-sheaf is just a functor from the category of K-algebras to the category of sets. A sheaf is a pre-sheaf satisfying the following sheaf axioms. If I start out with a tuple in the product over I of the f of bi's, such that Si restricted to Bij equals Sj restricted to Bij for all I and j, then there exists a section over A such that the restrictions of each Bi is Si for all I. And here, Bij is just a nice shorthand notation for Bi tensored over A with Bj. And this restriction notation is really denoting the image of the functor under the map induced by the map from Bi to Bi tensored over A with Bj and so on. So these are just the restriction maps. An equivalent, really nice way to phrase this is that the sequence going from Fa into the product over I of f of bi's, and then into the product over i's and j's of f of bi tensored over A with Bj, which in particular can go two different ways, must be exact. That is to say that the things inside here, such that the image going in one arrow agrees with the image going the other arrow, are exactly the things that come from here. So this is a nice, succinct way of stating the definition. And this is one possible definition of a sheaf in this extended category. There are several other possibilities, depending on the kind of topology and the kind of richness you want to include in the picture. This is, in particular, a sheaf in the FPQC topology. And the different topologies and things that you can do here is something that you'll talk about a lot more in an advanced course on, say, growth and dig topologies or autocollinology or something like this. But we don't want to have to define any of that, and we definitely don't want to have to try to define a stack or anything like this. So we're trying to sweep most of this under the rug and just define a pre-sheaf and a sheaf in the following fashion. But hopefully this explanation, beginning from the definitions of sheaves and pre-sheaves for topological spaces, has made these things feel a little bit more motivated to you. Now back in that topology land, one of the most important operations you can do is to sheafify. That is, you start out with a pre-sheaf and you come up with a sheaf which is as close as possible to the pre-sheaf that you started out with, while still being a sheaf. That's something that we'd like to do here as well. To begin, let's just consider a pre-sheaf. That is to say, just a functor from the category of K-algebras to the category of sets. Then the sheafification of F is a sheaf, which I'm denoting as F superscript SH for sheafification, and which satisfies the following universal property. It has a natural transformation from f to the sheafification, f sheaf, and if I have any other natural transformation from f to a sheaf g, then that natural transformation has to factor through the sheafification. In other words, the sheafification is kind of the smallest sheaf that f can map to. And one thing that we can show is that the sheafification of a pre-sheaf always exists. To prove this, we construct the sheafification from a pre-sheaf explicitly. So let's start out with a pre-sheaf. Then let's define a new sheaf, f prime. And its value at a particular ring R is the same as f of R modulo a certain equivalence relation, where two sections are equivalent if and only if there exists a faithfully flat extension where the corresponding restrictions are the same. Notice that when we do this, two things automatically happen. First of all, f prime automatically satisfies S1. In particular, we have the uniqueness property, so we're halfway there to becoming a sheaf. The second thing is that if I have any morphism from f to a sheaf g, then it's clear that this will have to factor uniquely through f prime. Where here this map from f to f prime is just taking an element to its associated equivalence class, so it's the most natural transformation in the world. To finish off the construction, we define the sheafification at R to be the limit over all faithfully flat extensions R prime of R of the kernel of the map going from f prime of R prime to f prime of R prime tensor over R with R prime. The kernel here is exactly the collection of elements in here which map to the same place under the two different ways that we can map them. The second property automatically makes us satisfy S2 and S1. And furthermore, it preserves the property that any morphism or any natural transformation from my pre-sheaf to a sheaf must factor through the sheafification, f. Where here the map from f to f, that is the sheafification of f, is the one corresponding to the associated limit. So this constructs the sheafification and proves that the sheafifications exist. Now one reason why we care about sheafifications is because representable functors will necessarily be sheaves. So for example, if I think about my affine group GLN, it has two subgroups, specifically SLN, which is the subgroup of matrices with determinant 1, as well as its center, which is going to be GM. The functor f, which takes a K-algebra R to SLN R times GMR, is going to send a K-algebra R to a group. So this is a group-valued functor. However, this is not a group scheme. And why is this not a group scheme? It's because it's not a representable functor. However, its sheafification will be a functor, and in fact turns out to be GLN again. One way to see this is to note that this is because if I've got an element of GLNR, then in some ring extension, specifically the extension where I can take the nth root of the determinant of G, I know that G over lambda will be in SLN R prime, where R prime is that ring extension, and lambda will be in GM R prime. This means that I can write GLNR as the union over all faithfully flat extensions of SLN R prime times GM R prime intersected with GLNR. And in general, we have the following theorem. Let's go with proposition. If f is a subfunctor of a sheaf G, and for every R, GR is the union over all faithfully flat extensions R prime of R of the intersection of GR with FR prime, then G is the sheafification of F. And the proof of this is really clear. It's just very easy to check that a sheaf G satisfying this property automatically satisfies that universal property we talked about for the sheafification. In particular, if I start out with a natural transformation from my pre-sheaf f to some sheaf h, I can extend that to a natural transformation from my sheaf g to my sheaf h in an obvious way. In particular, given some a and gr, there's some faithfully flat ring extension r prime of r that contains a inside, such that a is inside of such that a is inside of f of r prime. What this really means is that a restricted to r prime is an f of r prime, and therefore a restricted to r prime is in the equalizer of the diagram, or the kernel of the equalizer diagram from fr prime to fr prime tensored over r with r prime. This means t of a restricted to r will be inside the kernel of the equalizer diagram associated to t. And because, t of a restricted to r will be inside the kernel of this equalizer diagram associated to h, because t is the natural transformation from f to h. But since h is a sheaf, this implies that there exists some section over r for the sheaf h, let's call it b, so that when b is restricted to r prime, it's equal to t of a restricted to r prime. And what we're going to do is we're going to define the natural transformation t twiddle from g to h to send our a to our b. And it's very simple to check from here on out, now that you know that where everything goes, that this is the unique extension which factors the natural transformation from g to h. From f to h through g. So because h satisfies this universal property, because g satisfies this universal property, we have to conclude that g is the sheafification. So this is just one example of a sheafification, and in this particular case, I took a very natural pre-sheaf, one which is group valued and everything, and where we were hoping that maybe I was getting something which is a group scheme, and I didn't. But the sheafification did give us a group scheme. And this is something that we pointed out last time we spoke, our last video lecture, that is to say, when I'm looking at a way of defining the product of two group schemes, in particular two subgroups of a group scheme, it's not the natural definition that springs to mind. It's not the naive definition, because that defines a functor which isn't necessarily going to be representable. But it turns out that when we sheafify that functor, we get exactly what we needed. And this process of sheafification allows us to very explicitly define sheaves, not even just sheaves, but also various affine group schemes whose existence we proved before, but possibly relate them to their more intuitive counterparts. One really nice example of this is the quotient. So let's consider an affine group scheme G with normal subgroup N. We know there exists some affine group scheme which we call G mod N, and which is defined in terms of some sort of universal property again. But we just proved that this group scheme exists abstractly without any real relation to the corresponding quotient group which naturally lies around. But it turns out those, of course, are related through sheafification. In particular, the quotient group G mod N, which is an affine group scheme, is the sheafification of the pre-sheaf, which does our sort of natural quotient for us. So this is a group valued pre-sheaf, and its sheafification is going to be the affine group scheme G mod N. To prove this, let's think about that process of sheafification. One of the first things we did was we constructed a new sheaf, f prime, from f by modding out by a certain equivalence relation, where we said two things are equivalent if they end up being identified under some flat and faithful extension. But it turns out that here we don't even need to do that. In particular, it already holds. So quotienting out by the corresponding equivalence is not going to do anything. In particular, if I have an injective map of k-algebras, R to R prime, then the corresponding map of functors from f of R to f of R prime will automatically be injective. Proving this amounts to showing that n of R restricted to R prime, that is to say all the sections in n of R restricted to R prime, that set is equal to n of R prime intersected with the set G of R, all sections of G over R restricted to R prime. Now nR has some embedding into affine space over R, and therefore it can be written down as the zero set of some collection of polynomials. Using extension by scalars then, nr prime will be the same zero set, but inside the extended coefficient ring. Since the inclusion of R into R prime is injective, and since the relations are the same, anything in nr, which is 0 in nr prime, was already 0 inside of nr. So this proves the desired injectivity. This means that the sheafification is just obtained by taking the limit over faithfully flat extensions of the kernels of the equalizer diagrams. And what we'd like to do is prove that this is the quotient of G by n. To prove this, let's remember that the quotient already exists. So I can choose an affine group scheme Q and a quotient map with kernel n. Then there's an obvious natural map going from our functor f to our functor q, which is a natural transformation and which is injective. Then for any faithfully flat extension, R to R prime, I can define K of R prime to be the kernel of the equalizer diagram, going from f of R prime to f of R prime tensored over R with R prime. If I combine this with the natural maps to Q, along with the fact that Q is automatically a sheaf and therefore has kernel of equalizer diagram given by Q of R, then an obvious diagram chase induces a natural map going from K of R prime to Q of R, not forgetting our arrow over here. And now if we notice that this arrow here is injective and this arrow here is injective, that forces this arrow here to be injective as well. So I have an injective homomorphism from K of R prime into Q of R for all faithfully flat extensions R prime of R. And now if I go ahead and take the limit, I end up with a natural injection going from the sheafification of R, which is the limit of the K of R primes, into Q of R. And now to finish this off, we can think of our map from G to the sheafification as functor, and then on to Q. We also have a map from G to Q, and from the definition of the quotient, I know that my function from G to Q here has to factor through this in a unique way so that the diagram commutes. This automatically implies in particular that the map from the sheafification of f to q is surjective, and therefore this is an isomorphism. This completes the proof. So that's probably a pretty good stopping point for today. But one of the main points that we have here is that we're taking our intuitive ideas of how to construct things like products of groups or quotients of groups and these sort of things, and we're learning how to extend them into the group scheme situation. And one of our main tools here is sheafification, which is allowing us to take something which is not representable and potentially obtain something which is representable. So when you're faced with something, for example, a quotient, and you're not quite sure what it might be, it's always a good idea to think about, okay, well, what does this sheafify to? But yeah, let's go ahead and stop there for now, and I'll see you guys next time.